Okay, so good morning everyone. Actually from CFL, that is context-free languages, 2-3 points have remained. Okay, so today we'll complete that and then we'll finish our this unit. Okay, so those points are what? The first is what? Closure properties of CFL. Of CFL, context-free language. Okay. So in regular languages, what we have seen, the regular languages are closed under union, concatenation, and clean closure. Okay. So let us attempt to prove these facts using CFG. Okay. So here what we have to prove that CFL are closed under union, concatenation, and clean closure. Okay. So first theorem, write down. The first theorem here is what? If L1 and L2 are CFLs, if L1 and L2 are CFLs, then their union L1 union L2 is also a CFL. Is also a CFL. Okay. So what is the theorem that we have to prove? If L1 and L2 are CFLs, then their union is also a CFL. So in other words, what is this theorem? CFLs are closed under union. Okay. CFLs are closed under union. Okay. So what we'll do here, let CFL is what? The language generated by that context-free grammar. Okay. So let us consider L1 is a language generated by grammar G1. Okay. So let us represent this. Let G1 is a grammar and let L1 is a what? The language generated by G1. So this is a CFL. The L2 here is a what? The language that is generated by the grammar 2. Okay. So we know that grammar is denoted by 4 tuples. So for the G1, we'll use the notation let V1. V1 is a what? Set of non-terminals for the grammar G1. T1 is a set of terminals for the grammar G1. Let P1 indicates the production rules for the G1 and let S1 is a start symbol for this G1. Similarly, for the G2 will represent it by the 4 tuples, set of non-terminus, set of terminus, set of production rules, and the start symbol. Okay. So what we have to prove now? We'll take the what? Union of L1 and L2. Okay. So let L3 here is a what? Now what is our L3? L3 here is a what? The language for the G3. Okay. So G3, how will represent G3? Let G3 is equal to what? 4 tuples V3, T3, P3 and S3. So what we want? This L3 to be union of L1 and L2. Okay. So whenever we'll take L3 as a union of L1 and L2, after taking that, it should be a CFL. That we have to prove it. Okay. So what will be our V3? G3 is equal to V3 is a what? Set of non-terminus for the grammar, that is G3. Okay. So what we'll do? We'll take the union of here V1 and V2. Okay. So V3 here is a what? Union of non-terminals of the grammar G1 union V2 non-terminal set of the grammar G2, and here as well as what you have to add? You have to add the start symbol of this new grammar. Okay. So what is V3? V3 is this set V1 union V2 union S3. Similarly, T3 will be what? In this case, T3 will be T1 union T2. Okay. Now the production rules. So whenever you concatenate, we have added a new non-terminal S3. So we have to also add a new production. Okay. So P3 here is a what? P1 union P2 union, one new production we have to add, and that production here is what? Let I'm writing here S3. We have to take the what? Union. So union means what? S3 will be S1 or S2. This new production will add. So we'll take all the productions from the grammar G1, that is P1, all the productions from the grammar G2, that is P2, and one new for the union we are taking S3 as a what? S1 or S2. Okay, and comma S3 is your start symbol, that already we have seen. So this is our what? New grammar. Okay, so it contains all the productions, and these two only newly added productions. So you know that after this it remains a context free grammar. Okay, we'll take also the example of this. Let for the G1, the example is let S1 derives A, S1 B or AB. Okay, can anybody tell me the language generated by this? What is the language generated by this? This is our G1. You can type it in the chat window. What is the language generated by G1? What is the language generated by G1? What is it? S1 is start symbol, AS1B or AB. Minimum length string here is a what? AB of length 2. Okay, the next string is AABB, that is correct. Okay, generalize. Now you generalize. Yeah, Athara, that is correct. So what is the language generated here? Okay, what is the language of this? A raised to n, b to the power n, that is our L1 here. Okay, that is correct. Equal number of A's followed by number of B's. Okay, but it should be equal, no? Yeah. And what is the value of n? N should be greater than equal to 0 or greater than equal to 1? N should be greater than equal to 0 or what? Greater than equal to 1. Yeah, it is greater than equal to 1 because minimum length string here is 1. So n is greater than equal to 1. Okay, so this is the language and this is what? The grammar for this. Okay. Okay, so we have considered G1. Now let us consider the G2. Let G2 is G2 here is start symbol is S2. We assume S2 derives let AB S2. See how I am changed this AB S2 or AB. Now tell me the language L2 generated here. What is the language generated here? Minimum length is AB here, but what is the language generated here? Yes. Other students, what is the language generated here? You should be able to generalize now. What is the way to generalize? You go on finding the strings generated till you can generalize it. Yeah. So language generated here is what? AB to the power n. And n here is also greater than equal to 1. Okay. So we know now what? These two are the context free languages. Yeah. Because we can write a context free grammar. Okay. So G1, G2 are the context free grammars and their languages are L1 and L2. So now we'll consider now G3. So what we have to do in the G3? In the G3, new start symbol is added and we have to take the union of these two. Okay. So to take the union of this, what we have done? S3 generates S1 or S2. This is the union of G1, G2. S1 or S2. And then S1 productions as it is, S1 derives AS1, B or AB. And we'll also write what? S2 derives what? AB, S2 or AB. Okay, note down this examples properly because for the next proper theorem also we'll use the same examples of G1, G2. Okay, so this is what our G3. Okay, so now is it a context free grammar? This is my question, whether G3 is a context free grammar. whether it is a context-free grammar. You know the rules for the context-free grammar. What types of rules are there in the context-free grammar? A derives alpha. On the left-hand side of the production, only non-terminal is allowed, and on the right-hand side, it is a sentential form. Yeah. So is it a context-free grammar? Is G3 a context-free grammar? Sorry, I was muted. Okay, now am I audible? Okay, so is G3
Yes,
a context-free grammar? Yes. Okay. So after taking the union of G1 and G2, G3, we got new grammar, and the language generated by G3 is a context-free language. Yeah, so it is a context-free language. Okay. So what is the language here? What is the language here? It is A to the power n, B to the power n, or AB. This is the language. Okay. So this type of strings are generated using the G3. Okay. So we have proved the first theorem. What was our theorem? If L1 and L2 are context-free languages, then L1 union L2 is also a CFL. Is that clear how we proved the theorem using the example? Yes, so that we'll go for the next property. Okay, so next property. Next property. Write down. If L1, this next theorem, if L1 and L2 are CFLs, if, just a minute. If, second theorem is what? If L1 and L2 are CFLs, then now we have to prove concatenation. Same way as we proved in the earlier theorem, we'll prove here also. L1 dot L2 is also a CFL. Is also a CFL. Okay, we'll do the same thing. Can you prove it now? What we have to do? Like in earlier we proved, same way. What we have to do? I will not write this part again. Here it is clear. Now instead of L3, L1 union L2, what we have to do? L1 concatenation L2. Okay, we'll do the same thing. Let L1 is a language generated by grammar G1. Let L2 is a grammar generated by the, language generated by the G2. G1 is this, V1, T1, P1, S1. G2 is this. L3 is a language of G3. And now, what is G3? What we have to do? Can anybody tell me the changes here? What will be my G3? Is it is V3 is same? We'll take the V1 union V2 union S3. Yes. Yes, can anybody help me in writing G3? G3. Here we'll take same V1 union V2 union S3, new start symbol for the grammar G3. T1 union T2, that is union of terminal sets of G1 and G2. And now production rule here. P1 union P2. Okay, union P1 union P2 union. Which production here I have to add? Can anybody tell me? Which new production rule I have to add here? Union ke liye which production rule you will add? S3 derives what? Simple है. यहाँ पे question is simple. Union में हमने क्या? Which production we added? S3 derives S1 or S2. Okay, concatenation mein here which production I have to add here? S3 derives what? Concatenation के लिए क्या करना होगा? S1 dot S2. Yes. This is the only change to prove the concatenation. Okay. So the same example, let G1 is S1 derives A S1B. I'll take the same example where we have seen language L1 is A to the power n, B to the power n, and n is greater than equal to 1. Similarly, what I have to do here? G2 is S2 derives AB S2 or AB, and the here language L2 is what? AB to the power n, where n is greater than equal to 1. Okay. So what is our G3 now? G3 concatenation of this two. So we have added the new production. S3 derives S1 dot S2. Remaining things are same. S1 derives what? As it is A S1B or AB, and S2 derives what? AB S2 AB. What is the language generated here? What is L3? L3 is language generated by G3. Can anybody tell me? What is the minimum length string generated here for the G3? Minimum length string generated using this start symbol. Now S3 is our start symbol. Yeah, minimum length is AB, correct? So what is the language next string? AB, after AB, which string I can generate? Can I generate AB? Yes. So this is of length 4, then 6. Yeah. I can also generate no AB. Okay. So you can generalize this L1 dot L2. It is what? L1 dot L2 is what here? So L3 is equal to L1 dot L2, and L1 we know it is A to the power n, B to the power n, and this is followed by AB full power of n. So here we have proved that what? L3 is also a CFL. We can write a context-free grammar for it. So L3 is a CFL. Okay. So second theorem we proved that if L1 and L2 are CFLs, then their concatenation is also a CFL. In other words, what? CFLs are closed under concatenation. Okay. So what is the second property? CFLs are closed under concatenation. Are the two theorems clear? The first we have seen CFLs are closed under union. Second, CFLs are closed under concatenation. Third theorem now will prove the theorem number 3. Theorem number 3, write down. If L, now we have to consider closure. If L is a CFL, then we know how the clean closure is represented. L star. L star is what? 0 or any occurrences of L that you know. Okay. So if L is a CFL, then L closure, how we read this? Clean closure, Clean closure of L. If L is a CFL, then L closure, it is also a CFL. Is also a CFL. Okay. In other words, what? CFLs are closed under clean closure. CFLs are closed under clean closure. Okay. So here what we have to consider only one grammar, no? Because L we consider, let L is a language generated by grammar G. Okay. And let G is denoted as a what? VTPS. So as we are considering only a single grammar, I have not used the suffixes V1, T1. Okay. So VTPS. Okay. What we have to prove that? L closure. Okay. So our new grammar. So let we use the same terminology. Let G3 is equal to V3. Okay, I'll write first and then we'll consider what will be the V3, T3, P3 and S3. So here V3 set will be what? We have to take the what? Closure of this. So it is V union. We are going to add the new non-terminal. So S3, V union S3. Then T3 is T only. Terminal set is same. Or we have to add epsilon if epsilon is not there, as we are going to take the closure. Closure also contains epsilon, that you know. So T union epsilon. Then P3 is what? P union. Here, which two productions we have to add for the closure? Can anybody tell me? See, here I am considering. If I am considering A closure, what is the language generated here for the A closure? What is the language here generated for the A closure? What is it? 0 or any occurrences of A? Yeah. So and n is here greater than equal to 0. That is correct. It is A to the power n, where n is greater than equal to 0, as epsilon is also there. So A closure is what? Epsilon A. We know that any occurrences of A. So it goes infinite. Okay. So here for the closure, what we have to do here? See, S3 derives. For the closure, what I am doing? See, S is our start symbol of this L. Okay, so S, I am using the recursion. See, S3 or epsilon. These two production rules are newly added for the closure operation. See, for the closure here, for the A to the power n, how the grammar is written? Let A derives A, S or epsilon. Same thing we did here, S, because our A here is L and L start symbol is S. So what I did? S followed by S3 or epsilon. So this is our what? New production rule set, comma. S3 is our new start symbol. Okay. So we'll take one example here. We'll take here this only. S1 का जो हमने लिखा था, S1 derives A S1B or AB. Okay, so what is our G? G, S here is A, S, B or AB. So we know this is the language. What? The language of G here is A to the power n, B to the power n, where n is greater than equal to 1. Okay, so we know that what? This is not generating epsilon. Yeah, this L is not generating epsilon. But when you take the closure of this, it should generate the epsilon. Okay, so what is our G3? G3 is what? S3 derives S, S3 or epsilon. And S is as it is here, we'll write ASB or AB. So is it a CFL now? Is the language generated by G3 is a CFL? This is a closure. For the closure, these two production rules we have newly added. so that we can get the closure of this. Okay, so this is a closure. So language generated by G3 is a context-free language. Okay, so what we have proved here, if L is a CFL, then L is a CFL, then its closure is also a CFL. Okay, so we have proved all the three theorems for the CFLs. These theorems we have also proved for the regular languages. Okay, so are the three theorems clear? So that we'll go for the next point. The first, what we have seen, if L1 and L2 are CFLs, then its union is also a CFL. Okay. Second theorem was what? If L1 and L2 are CFLs, then its union is also a CFL. And the third theorem we proved is what? If L1 and if L is a CFL, then its closure is also a CFL. Okay. So now we'll go for the next point. Derivation graph. Okay. We have already used the derivation tree. Okay, so we have seen derivation tree is what? It is the graphical representation of the derivation of the string. And in the derivation tree, what? The internal node is a non-terminal and leaf nodes are the terminals. Okay, and we also seen that the root node is a start symbol. Okay, and we know that parse tree, as it is a tree, derivation tree is a tree, it is not containing any cycle. Okay, so derivation tree, here we have seen derivation tree, but that can be used only for the type 1 and type 2 grammars. Derivation tree can be used for the type 1 and the type 2 grammar. Why? Because we know that in the type 1 and the type 2, on the left hand side of the production rule, only one non-terminal is allowed. We have seen A derives alpha. This is what? This type of rules are allowed. Oh, sorry, 1 minute. This should be type 2. And this should be type 3. Type 2 and the type 3. Yeah. So in the type 2, it's a what? Context-free grammar in which all the productions are of the form A derives alpha. So on the left hand side, only one non-terminal is there. Okay, and the right hand side is a sentential form. So it can be easily represented in the tree. We have seen if my rule is this way, A derives ABC, then in the tree we show it like what? A derives A becomes the parent of this right hand side, each symbol, and each of the symbol on the right hand side, it becomes a what? It becomes a child of that parent. So this is how we represent in the derivation tree. And in the type 3, what? In the type 3 is also of this form, A derives. The left hand side is only one non-terminal, and on the right hand side, only one non-terminal is allowed, which can appear as a leftmost or the rightmost symbol. And depending on that, it is known as a what? Left linear or the right linear grammar that we have seen in detail. Conversion of right linear to left linear or right linear to the finite automata. Okay, so derivation tree, it is used to represent only for the what? Type 2 and the type 3 grammar. Now, what are the problems with the type 0 and the type 1? Type 0, so we have seen type 0, there are 4 types of grammar: type 0, type 1, type 2 and the type 3. Type 0 also known as a what? Unrestricted grammar. There are no restrictions on writing the production rule, and each production rule is of the form what? Alpha derives beta, where alpha and beta are the what? Sentential forms. These are the what? Strings of terminus or the non-terminal. Okay. So in case of type 0, what? My production rule can be of this way: A, B derives B, B, C. There are no restrictions on how to write rules in the type 0. So that's why it is unrestricted. So if this is the type of rule, we cannot represent that in the tree format. Okay. So here, that's why we are going to use here what? Derivation graph for type 0 and the type 1. I will take one example also of derivation graph. Okay. And in type 1 also we have seen the rules are of the form alpha derives beta. But here the restriction is what? Length of the beta, it should be at least as much as that of the alpha. It is also known as a what? Context sensitive grammar that we have seen. Okay. Type 1 is also known as a what? Context sensitive grammar. Type 0 and type 1, these languages, these are accepted by the Turing machine that we have seen. Type 2 is accepted by non-deterministic push-down automata, and type 3 is accepted by the finite automata that we have seen. But now we are considering derivation graph. Okay, because of this type of production rule, as on the left hand side sentential form is appearing, we cannot represent type 0 and type 1 using derivation tree. Okay, so we are going to use a derivation graph. So what is a derivation graph? Okay, so derivation graph, here it is a directed planar graph. Anyone knows about definition of planar graph or planar, whatever? What is the planar graph? Derivation tree, derivation graph, it is a directed planar graph. Okay, anyone knows about the planar graph? What is it? What is the planar graph? Anyone knows about it? Okay, so it is a what? It is a graph. It can be drawn on a two-dimensional plane without intersecting any two edges except at the nodes. Okay, so I'm repeating. What is a planar graph? It is a graph which can be drawn on a two-dimensional plane without intersecting any two edges except at the nodes. Okay, so how to draw here the in this graph? So if my productions, let P productions, these are number, each production will give the number that we let the production rules are 1 2 3 up to what? Let K. So 1 2 3 up to K. Let there are K production rules, and let we know that here the rules are of the form alpha derives beta. Okay, let this alpha, it contains the symbol alpha 1, alpha 2 up to alpha m, and let beta contains the symbol, let beta 1, beta 2 to beta m. Okay, then in the planar graph, let this is represented using let the rule number K. Okay, then we'll draw like this way. So name of the node here is the rule number, that is the K. And for this K, whatever symbols appearing on the left hand side, it forms the incoming edges. So my incoming edges are for the left hand side, alpha 1, alpha 2 to alpha m. And outgoing edges will be for the right hand side symbols. Okay, so outgoing edges will be here beta 1, beta 2 up to what? Beta n. So this is how we'll represent it in the directed graph. Okay, is that clear? I will take one example of the directed graph, drawing the directed graph. I will take one example of the type 0 grammar and we'll draw the directed graph. You note down here, is it clear here? How to draw the edges in the derivation graph? Yes or no? So we'll take the type 0. Okay. Whether you have finished writing, all of you, so we'll take the example. Directed graph is a what? Planar graph in which you can draw it on a two-dimensional plane without intersecting any two edges except at the nodes. So each rule is given a number and that number forms your node, for which the incoming edges are the what? Left hand side symbols, and outgoing edges are labeled by the right hand side symbols. That is what the concept here in drawing the derivation graph. So we'll take the example of the derivation graph. So I'm considering here the type 0 grammar. Okay, so let G is a grammar with the non-terminus S, A, B, C, D. This is my non-terminus set. Let the terminal set is A, B, and plus production rules one by one will write. So I'm writing here let P is the set of production rules and let S is a start symbol. Okay, so let P consist of, okay, so I'm writing here let rule number 1 S derives ACS. In detail, it is not in your syllabus about type 0 or type 1, but you should know it. So I'm taking the example in detail. What is expected? You should know the context-free grammar in detail. Rule number 4, CA derives AC. So you can see here alpha on the left hand side. Rule number 5, let CB derives BC. Rule number 6, DA derives AD. Rule number 7, DB derives BD. Rule number 8. So we'll not go in detail how it is working, and just for example, I have taken this. So don't go in detail about this. You can take any example, not necessary. 9, 10, 11, B derives P. Okay. So these are the rules. This is the grammar given, and let us consider. Okay, the question here is what? Again, it is difficult to find that which type of language. Actually, you have to derive it and check that which kind of strings can be generated using this grammar. But I know one example, so I'm taking that. That is, you can derive here AB plus AB using this grammar. So what is the question here? That you have to draw the derivation graph for this given string. Okay, you have to draw the derivation graph. So what we'll do, we'll first derive the string. At each step we'll write the rule number, so that using that rule number you can draw the derivation graph. Okay, so let us derive the rightmost derivation. So know the meaning of rightmost derivation. At each step in a derivation, the rules are applied to the rightmost non-terminal first. Okay, so who will tell me the rules? Can you guess the rule? First rule, which rule I have to apply here? As it is not simple here like context-free grammar. Okay, so I'll apply directly here. Let S derives ACS, because if you start with let BDS or any other, you may not derive the required string. Okay, so let A derives ACS. This is my rule number 1. Okay, next rule here. Which rule is to be applied now? Because rule number 3 is for S, there are 3 ways. S derives plus, S derives BDS. Which rule should I apply here? Can anybody guess? Rule number 1 or 2? Which rule should I apply here? Okay, rule number, let me try, as all you are saying rule number 2. AC. So we'll, as it is a rightmost derivation, we know that rightmost non-terminal rule is applied to the rightmost non-terminal first. So S derives, we'll replace it by S derives BDS. So it is a rule number 2. Okay. Next step, can anybody guess which rule now should apply? We want the string AB plus AB. The string to be generated is AB plus AB. Okay, so let me apply the rule number 3 for this, and let me check whether we are getting the string. A, C, B, D, S derives plus rule number 3. Okay. So now here, what we want, B at the end, And if I consider rule number 8 is what? D plus derives plus B. Okay, so what we have to do here then? This D plus will replace it by its right hand side, that is plus B. So in the next step I am applying the rule number 8. So A, C, B, this is as it is, and D plus is replaced by the plus B. That is the rule number 8. So we got plus B, but what we want? Plus AB. So if I check the rule B, there is no rule for B plus. Yeah, rule number, Divya, let me check. Rule number 5 is what? CB derives BC. Yeah, let us apply and check. So next step we'll apply the rule number 5. So rule number 5 is what? This CB will replace it by BC. So we'll get ABC plus B. After applying CB derives BC. Next step. Now here you can check which rule now you can apply easily. C plus, yeah, that is the rule number 9. Correct. Rule number 9 will apply. So rule number 9 is C plus. Yeah. C plus is replaced by what? AB plus AB. We got now this. Yeah. Rule number 9 के बाद we got AB plus AB. Now it is simple. Now next step में who will tell me it is simple now. We got this plus AB part. Yeah. Rule number first will apply rule number 10. No, rule number 11 will apply as rightmost derivation hai. So first we'll replace rightmost non-terminal B by this B. And then last step we'll apply rule number 10. So this A is then replaced by the AB. And now we have derived the string. So we applied rule number 1, 2, 3, 8, 5, 9, 10 and 11 and 10. So this is a derivation, but now we'll draw the derivation graph. So you know the derivation graph. So first step is what? First rule we applied is, now you tell me, first rule applied. So what is my node here? 1. What is the incoming edge for this rule number 1? Incoming edge will be labeled by how many symbols? In the derivation graph, how we are drawing? Incoming edges are for the left hand side. Yeah, एक ही incoming edge आएगी. No? See, S derives ACS. So incoming edge will be only for S. And that is correct. Now you are saying outgoing edge. There are 3 outgoing edges. That is, each of this is labeled by A, C and S. Is that clear? What we did, is that clear? Is that clear? Yeah. Next step में क्या करना है? What is rule number 2? S derives BDS. So incoming edge will be for what? S, correct. And rule number 2 is the new, correct. And outgoing edges from this number 2. Outgoing edges for this number 2. BDS, correct. B, D, yes, correct. Next, what is the rule that we applied? Next, rule number 3. So rule number 3 is what? Rule number 3, and I'll draw like this way. Outgoing edges plus. S derives plus. So this indicate what? S derives plus. Next is rule number 8. What is the rule number 8? Rule number 8 के लिए see, what are the incoming edges? We have to create a new node. Can you tell me the incoming edges for the D? Rule number 8 के लिए incoming edges for the rule number 8? Yeah, D plus. So D plus, I am connecting this. D plus. And outgoing edges are? Outgoing edges are plus B. Yeah, outgoing edges are plus B. Yeah, correct. Next step, after rule number 8, what we did? Rule number 5. Rule number 5 is what? What is the rule number 5? CB derives BC. So CB derives BC. Rule number 5. I'll create here new node 5. Incoming edges from C and B. Outgoing edges are B and C. नेक्स्ट रूल नंबर कौन सा हो गया अभी अपना 5. रूल नंबर 9 के लिए क्या करना होगा 9 इनकमिंग एजेस आर फॉर complete the graph. Yes, C plus and rule number is 9 and outgoing edges are C plus का right hand side क्या है plus A. Yeah. Rule number 9 complete हो गया. Then we'll apply what? Rule number 11. So rule number 11, it is simple. It is what? B derives B. Okay. And then what remains? Rule number 10. A derives A. Here it is different. Here you can see the edges are labeled by non-terminals or the terminals. And the nodes are labeled with the production rule number. Okay, rule number. Okay, so now this is complete. So we have to add the nodes for this incomplete edges. So each of this will add here at the end epsilon once our string is derived. This is AB. So each of this you complete with the epsilon. So this is what our derivation graph. Complete किया सबने? So that I will consider the next point. Completed or not? Graph, all of you. Yes, so that I'll take the last point from this unit. Completed or not? Put yes or no so that I'll move. Okay. So last point is generally what? Why we are studying this? Why we are studying context-free grammar? Meaning is what? We are considering now what? Applications of context-free grammar. Okay. So context-free grammar, as we know that each language has a grammar. Okay. We have seen the natural language grammar is different as the same sentence can have different meaning depending upon the situation. Here we are considering programming language, and for programming languages, to check the syntax of the programming languages, most of the programming languages uses what? Context-free grammar. Okay, so context-free grammars are used to denote the syntax of the programming languages. So we'll consider the example for the C language. For any language you can consider. Okay, so we know that compiler, the function of the compiler is what? It takes the input as a high level language program, which is also known as a what? Source program, and generate the output as a what? Target program, which is a machine language. Okay. So in compiler, already we have seen the lexical analysis phase. The lexical analysis phase, which takes the input. This is the first phase. There are 6 phases. Lexical analysis, syntax analysis. Will not write in detail. Let us consider how. Then semantic analysis. Semantic analysis. Intermediate code generation, code optimization, and finally code generation. Finally what? Code generation. So these are the 6 phases of the compiler. First phase, output of each phase is given as an input to the next phase, and the output of last phase is the your target program. And this lexical analysis, it takes the input as a source program. Okay, so these are the 6 phases. And what we have seen, the first phase, it uses the regular expressions. That last chapter or last unit, we have seen how the regular expressions are used in the lexical analysis phase to generate the tokens, because the lexical analysis function is what? It reads the source program character by character and generates the output as a tokens. And we have seen token is a what? It is the smallest entity in the program. And token can be what? In programming languages, the tokens are what? Identifiers. It can be keywords, can be constants, can be operators, punctuation symbols, or it can be a string, it can be comment, but those things are ignored by the lexical analysis. It will read your program character by character. It will check the category which is matching using the regular expression. So we have seen for each of this, there are the regular expressions to represent the token. So once the tokens are generated, these tokens are given as an input to the next phase. That is the syntax analysis. So what is the function of the syntax analysis? As the name indicates, it will check the syntax of your input, whether your input or program is syntactically correct or not. And for that purpose, it uses the context-free grammar. Okay. So second phase of the compiler, it uses what? Context-free grammar to check the syntax. And if your input is syntactically correct, then it will generate the output as a parse tree. So we know the parse tree. Okay. So there will be here grammar. That grammar will check the syntax of your input. If that is syntactically correct, then output generated here is a parse tree. Okay. And then after checking the syntax, then the next phase start. Okay. So we'll not go in detail. Then here the semantic is checked, then intermediate code is generated, then your code is optimized, and then final phase, this code generation, it will generate the target program. Okay, so we'll take the example. Let my input A equal to B semicolon. Let this is the input to our first phase of the compiler, lexical analysis. Okay, so what it will do? We have seen identifier के लिए what is the expression? We have seen regular expression, letter followed by letter or digit closure, underscore may be used. We know that underscore is allowed in the identifier. So what does indicate? Letter. Letter is a small case or the uppercase letter. It is followed by what? Letter or digit closure. So your identifier, it should start with a letter. Letter means here small case or uppercase alphabet I am saying. Okay. Constant. Constant के लिए you can consider the expression like constant digit plus. Floating point के लिए I already told you can add the floating point, how it can be added, but it is optional part. So I can take dot plus question mark. Okay. So this is optional. This may or may not be there. So digit plus is one or any occurrences or digit followed by what? Dot is decimal point, D plus. But it is a question mark. Question mark means what? It may or may not occur. So if you want only 32, this part will generate epsilon. We have seen this. Huh? And if you want this part, then we'll consider like if I want 32.45, then dot 45, it will be generated by dot D plus. So this is what the expression for the constant. This is for the identifier. Then operators के लिए there will be the expression. Operators are the, we know, fixed operators are there. So you can have a, suppose this is your assignment operator, and operator के लिए suppose the expression is like operator is, let OP is a name given to that. So it can be let any operator. It can be minus, plus. Let I'm considering all the binary operators, minus, plus, assignment operators, division, multiplication. So let OP is a name given to this. Okay. So this is how what there are regular expressions used by the lexical analysis. Now, if this is my input, what the lexical analysis will do, it will read character by character. It will check which type of pattern or regular expression is matching for this input. Keywords के लिए क्या expression है अपना? Keywords are already fixed there, no? So let keyword is a name given to all the keywords. I already told keywords are fixed. So all this can be considered as a string. Let if is a keyword or else is a keyword. So like this way, all the keywords For is a keyword. Okay, so all the keywords can be considered as a string, and you can have a what or in between. So this is a regular expression for the keyword. So now here lexical analyzer will read A. It will check which type of regular expression is matching. So we know that operator is not matching, constant is not matching, keyword is also not matching. So this is recognized as a what? Identifier, because this expression is matching for this A. And what is the token generated? It may use the name, let it may use the ID as a name for this identifier A. A is recognized as a identifier. Okay, and that the token generated for equal to is let assignment operator, it is matched by the operator, and let it is equal to only. Let B is recognized as a what? Identifier, and semicolon is recognized as a, let semicolon will take as it is, let it is a punctuation symbol, it is matched by the punctuation symbol pattern. So punctuation ke liye again, like keyword punctuations are fixed. So punctuation can be here comma or semicolon or apostrophe or double quotation mark or parenthesis, okay, or the square brackets. So all those punctuation symbols can be written here using or, and punctuation symbols are the single character. So let pun, let this is a name given to all punctuation symbol. So this is what the list of tokens which is generated by the lexical analysis phase using the regular expressions. It is reading character by character, and it is checking which kind of regular expression is matching for that, and then it is generating a token. So these 4 tokens are generated here. Now what you will say, there is a space after A, there is a space after assignment, there is a space after this punctuation, there is a new line character. Lexical analysis, it ignores blank space, tab, new line character. No tokens are generated for those, that is blank space, tab, or the new line character. So only tokens generated here are what? Here in this case 1, 2, 3, 4. These 4 tokens are generated by the first phase. So this is the output after lexical analysis phase. It is generating only the tokens. It is not checking the syntax. Okay, so even if here the semicolon is not given by you, then it will not generate any error. What are the tokens generated in that case? ID equal to, that is assignment operator, and ID. So these 3 tokens will be generated in that case. So then who checks whether your semicolon is missing or you have written incorrect something or operator is missing? So those types of errors, syntax errors, these are handled by the syntax analysis, and for that it uses the context-free grammar. So these 4 tokens are given as an input now to your second phase, that is the syntax analysis phase. Syntax analysis phase. So now here to check the syntax of this, there should be the grammar. Okay, so let here the grammar is already there. Suppose there is a grammar like ID, O, ID, and then let punctuation. These are concatenated ID, O, ID, P. So what is O here? Let O generates assignment, and let P generates the punctuation symbol. So let this is our grammar. Okay, so what we'll do here, this is my input, ID equal to ID semicolon. What we have to do, can we derive this string using the existing grammar? Yes, can you derive this ID equal to ID semicolon? Is the question clear? Can you derive ID equal to ID using this grammar? Yes or no? Can you derive it? You can derive like what? Start with the start symbol. What we want, ID is there. We'll start with this ID. Let us, it is a leftmost derivation. ID is as it is matching. O is replaced by assignment. And then this P is replaced by the punctuation. So you have derived the string ID equal to ID semicolon. So it is syntactically correct. Is that clear? The function of the syntax analysis. Have you noted all this? So one point has remained. Mohakar madam, just 5 minutes. One small point has remained.
Okay, ma'am.
All of you have noted this or not? Is that clear? So for each type of statement, there will be the grammar like this way. This is a simple case I have considered. It will not be applicable if I give A equal to B plus C. Because A equal to B plus C ke liye what? This grammar cannot generate that A equal to B plus C. So there should be the grammar to generate those type of statement. Okay, so we'll consider that also. So यहाँ तक clear है what we have seen? The use of context-free grammar for checking the syntax in the syntax analysis phase of the compiler. Okay. But now see what is the problem here. So I'm considering the Baker's NOR form. So what we have seen up till now,